Hi, ladies and gentlemen. Let me wholeheartedly welcome you to the 8th session on ECT 204 Signals and Systems. Today we will see linear time invariant systems. This is a rather lengthy speech. It is organized into your learning outcomes, then the definition of a system and states, then what is an additive CT system, then what is a additive discrete type system, then we will see a homogeneous continuous time system, then we will see what is a homogeneous discrete time system, then we will see a combination of additive and homogeneous system. They are called linear systems. Then we will see the time invariance property of continuous time and discrete time systems. Then we will see a combination of both the linear and time invariant system, the so-called linear time invariant systems, around which much of the control system theory, signal processing, system theory, everything revolve. Then the summary of understanding. The learning outcomes in this session are you will learn what a system is and what the states of a system are. You will define both things. Then you will learn additive and homogeneous continuous time systems with example. Then you will learn about additive and homogeneous discrete systems with example. Then you will understand continuous time and discrete time linear systems with examples. You will then you will learn the time invariance property in discrete and continuous time systems. Then you will understand linear time invariant discrete and continuous systems. First of all, what is a state? What is a system and what is a state? A system is a collection of interacting or interrelated components or elements that are organized for a certain purpose. Okay, a system is basically a collection of interacting or interrelated components or elements that are organized together for achieving a certain purpose. For example, if you look at the whole switch, it is a system. It's an assembly of some electrical device and mechanical assembly devices. And that is the purpose of this assembly is to control the current flow. So it is a simple system. And the state of a system is basically they are variables of the system. If you observe at a particular time, you can predict the behavior of the system at a later time, say t plus. The simple volt switch has two states, namely the on state and the off state. So those are the two states of the switch, the simple system switch. So if it is now, it is at t equal to 0, if it is on, at a later time t plus, it can be turned off. Or if it is now off, it can be turned on later. So every system has some inputs and outputs. Now, what is an additive continuous time system? See, suppose these inputs and outputs are continuous time signals, then it's a continuous time system. A system has many inputs and many outputs. So those inputs and outputs, if they are continuous time, then the system is a continuous time system. A continuous time system is said to be linear if it is both additive and homogeneous. Now we are looking at a linear system. So it has to satisfy two properties. One is the additivity of the system and the other is the homogeneity of the system. The system, for a linear system to be linear, it should be both additive and homogeneous. A system is said to be additive if the response to the input x1t is a y1t and the response to x2t is a y2t and the response to the sum of the inputs x1t plus x2t is a y1t plus y2t, then the system is said to be additive. That is, suppose I have a system and if I have an input say x1t, if the response to the system is a y1t and the response to the system to x2t is a y2t, then if I give a sum of inputs say x1t plus x2t to the system, if the response is y1t plus y2t, then the system is said to be additive. That is, the response to the sum of inputs, if it is equal to the sum of the responses, then the system is said to be additive. See, this picture explains it. Like I have a continuous time system here that is driven by input say x1t, its output is a y1t. The same system is driven by x2t, the output is y2t. Now the same system is applied with the input x1t plus x2t. If the output is y1t plus y2t, then the system is an additive system. Now let us look at some simple example. Consider the simple system yt equal to xt plus xt minus 2. It is basically an accumulator. It accumulates the present value with some previous value. So suppose this is driven by x1t, then the response y1t will be x1t plus x1t minus tau. And if it is driven by x2t, then the output y2t will be x2t plus x2t minus tau. Now, if I give the combined input x1t plus x2t to this system, that will be x1t plus x2t plus x1t minus 2 plus x2t minus 2. This is nothing but x1t plus x1t minus 2 plus x2t plus x2t minus 2. Nothing, that is nothing but y1t plus y2t. So, this is an additive system. Now, let us look at another system, say yt equal to axt. This is a system that scales the input. I give some input xt to it, it is scaled by a constant a. Okay, that is a response to the system. Suppose I give an input x1t to the system, the response y1t will be a times x1t. Response to x2t will be y2t will be a x2t. The response to x1t plus x2t will be some y dash t, that is equal to a into x1t plus x2t. This is nothing but a x1t plus a x2t. That is nothing but y1t plus y2t. So this is also an additive system. Now I make a small modification, the same system, I make the system yt equal to axt plus b. There is a constant addition of a constant of b. That changes the behavior of the system a lot. Suppose I give an input x1t to the system, y1t will be ax1t plus b and y2t will be ax2t plus b. And if I give a combined input x1t plus x2t, the response will be y dash t will be a into x1t plus x2t plus b. This is ax1t plus ax2t plus b. This is not equal to y1t plus y2t, because y1t plus y2t will be a into x1t plus x2t plus 2b. That is not the same as y dash t. So this is not an additive system. Now let us look at another system, say yt equal to cosine of xt. So whatever input is given, the system returns the cosine value of that input. So let the input be x1t. So y1t will be cos of x1t and y2t will be cos of x2t. The response to x1t plus x2t will be cosine of x1t plus x2t. But this is not equal to cos x1t plus cos x2t. Cos a plus b is not the same as cos a plus cos b. So this is not the same as y1t plus y2t. So this is not an additive system. Now let us look at yet another system, that is yt equal to xt by xt minus 2. We know that it is a fraction, so we can easily say that even by observing it, we know that it's not an additive system. Anyway, let us try to give some input to this. Let us give x1t to it, and the response y1t will be x1t by x1t minus 2, and y2t will be x2t by x2t minus 2. The response to x1t plus x2t will be y dash t, that will be equal to x1t plus x2t by x1t minus 2 plus x2t minus 2. That is not the same as y1t plus y2t. So this is also not an additive system. Now let us think about an additive discrete system. Now, a discrete system is said to be linear if it is both additive and homogeneous. So we will see these conditions, additivity and homogeneity, separately. First, we will see the additive condition. The system is said to be additive if the response to the input x1n is y1n, and the response to x2n is y2n, and the response to the combination, say x1n plus x2n is y1n plus y2n, then the system is said to be additive. This is very similar to our continuous time system. I have a system that is discrete. Why it is discrete? Because the inputs are discrete and the outputs are discrete. So I give an input, say x1n, its response is y1n. I give an input x2n, the response is y2n. Then I give the sum x1n plus x2n. The response, if the response is y1n plus y2n, the system is said to be additive. So this picture explains it. I have a discrete system here to which I give an input x1n, the response is y1n. I have another system to which I give x2n, the response is y2n. I give an input x1n plus x2n, the response is y1n plus y2n. If that is the case, then it's an additive system. Now let us look at some examples. These are actually discrete counterparts of the earlier continuous time system. This is a discrete kind of accumulator where yn is equal to xn plus xn minus 1. This adds the present input with some previous input that is delayed by m units. So xn plus xn minus 1. Suppose I give an input x1n to this y1n will be x1n plus x1n minus m. And if I give an input x2n, the response y2 will be x2n plus x2n minus m. Now the response to x1n plus x2n will be y dash n will be x1n plus x2n plus x1n minus m plus x2n minus m. That will be y1n plus y2m. So this is an additive system, just like the continuous time system. Now consider another system yn equal to axn, just like the system yt equal to axt. This this system is scaling the input by a factor a. So the response to x1n and x2n are y1n is ax1n and y2n is ax2n. The response to x1n plus x2n will be y dash n will be a of x1n plus x2n. That will be ax1n plus ax2n. That will be y1n plus y2n. So this is an additive system, just like its continuous time counterpart. This is also an additive system. Now consider this system yn equal to axn plus b. We know that in the continuous time counterpart it was a non-additive system. So suppose I give an input x1n and x2 inputs x1n and x2n, then the responses y1n will be ax1n plus b and y2n will be ax2n plus b. So the response to x1n plus x2n will be y dash n will be a times x1n plus x2n plus b. This is not equal to y1n plus y2n, because y1n plus y2n will be a times x1n plus a times x2n plus 2b. So the two are not equal. So this system is not additive. Now consider another system yn equal to cos xn. This is a discrete counterpart of the system yt equal to cos xt. Now this system returns, suppose I give a discrete input xn to the system, it returns the cosine value of the input. So yn equal to cos xn. So the response to x1n and x2n will be y1n is equal to cos of x1n and y2n will be cos of x2n. The response to x1n plus x2n will be y dash n will be cos of x1n plus x2n. That is not equal to cos x1n plus cos x2n, because cos a plus b is not the same as cos a plus cos b. So this is not equal to y1n plus y2n. So this is not an additive system. Let us look at another system, yn equal to xn by xn minus 1. This is a fraction, so it cannot be an additive system. Anyway, let us try with the inputs x1n and x2n. So y1n will be x1n by x1n minus m, and y2n will be x2n by x2n minus m. So the response to x1n plus x2n will be yn equal to x1n plus x2n by x1n minus m plus x2n minus m. That is not equal to y1n plus y2n. So this is not an additive system. It's also not an additive system. Now, for a system to be linear, it has to be both additive and homogeneous. We have seen the condition of additivity. Now we have to see what a homogeneous system is. Now a homogeneous system, a system is said to be homogeneous if the response to the input xt is yt and the response to the input c times xt is cyt. Given that c is a complex constant, is a set of element of the set z, that c is a complex number, then the system is homogeneous. So what is the condition of a system being homogeneous? That is, if the input is xt, yt, output is yt, and if the input is c times xt, and if the response is c times yt, where c is a complex number, that you have to note very carefully, that c is a complex number, not a real constant. If this condition is met, then the system is homogeneous. Z is a set of complex numbers. Now I have a system here, a continuous time system to which xt is given, the response is yt. Now I multiply this xt by a complex constant c, cxt, so output becomes a cyt. So such a system is a homogeneous system. Now consider all these systems like xt equal to xt plus xt minus 2, our continuous time accumulator. That is a response to cxt will be y dash t, that is equal to c times xt plus xt minus 2, that will be c times yt. So this is a homogeneous system. Let us consider the system yt equal to axt, the one in which the input is scaled. Suppose the input is cxt, the response y dash t will be a times c times xt, that will be c times a times xt, that will be c times yt. So this is also a homogeneous system. Now consider the third system, that is yt equal to axt plus b. Suppose I scale this by c, in response to cxt will be y dash t, that will be a times c times xt plus b. That is not equal to c times yt, because c times yt would be c times a times xt plus cb. This is not equal to cyt, so this is not a homogeneous system. Consider another system, xt equal to cos xt. The response to c times xt will be y dash t will be cosine of cxt, that is not equal to c cos xt. So it is also not a homogeneous system. Now, what about a homogeneous discrete system? Just like the continuous case, a system is said to be homogeneous if the response to the input xn is yn and the response to the input cxn is cyn. Given that c is a complex constant, then the system is homogeneous. Z is a set of complex numbers. I give an input xn here, output yn here. I give the input Cxn here. If the output is Cyn, then the system is homogeneous. Now let us consider the system Yn equal to xn plus xn minus 1. This is a discrete time accumulator. The response to Cxn will be y dash n, that will be C times xn plus C times xn plus xn minus m, that will be C times xn plus C times xn minus m, that will be C times yn. So this is homogeneous. So let us consider the system Yn equal to Axn. The response to Cxn will be y dash n, that will be A times C times xn, that will be C times A times xn, that will be C times yn. So this is also a homogeneous system. Now consider the system Yn equal to Axn plus b. So the response to Cxn y dash n will be A times C times xn plus b. This is not the same as C times yn, because C times yn would be C times A times xn plus C times b. So this y dash n is not the same as Cyn, so it is not a homogeneous system. Now consider the system Yn equal to cosine of xn. The response to Cxn will be y dash n, that will be cosine of Cxn, that is not equal to C cos xn, so this is not equal to Cyn. So this is also not a homogeneous system. Now we come to the major classification. What is a linear system? Now a linear system is one in which it is both additive and homogeneous is a linear system. A system that is both additive and homogeneous is called a linear system. In a continuous time system driven by x1t that yields y1t, x2t yields y2t, and if C1 x1t plus or minus C2 x2t yields C1 y1t plus C2 y2t, given that C1 and C2 are complex constant, then the continuous system is linear. That is, this is the principle of superposition. Basically, both the additivity and homogeneity. Additivity includes the negative sign also. Both additivity and homogeneity are included in the single equation. If the response to x1t is y1t and the response to x2t is y2t, and if C1 x1t plus C2 x2t yields C1 y1t plus or minus C2 y2t, given that C1 and C2 are complex constant, then the CT system is linear. If a discrete time system, for a discrete time system driven by x1n, if that yields y1n and x2n yields y2n, and if C1 x1n plus or minus C2 x2n yields C1 y1n plus or minus C2 y2n, given that C1 and C2 are complex constants, then the discrete system is said to be linear. This is called the principle of superposition. Say yt equal to cos xt, yn equal to cos xn are non-linear because they are non-additive and non-homogeneous. Yt equal to axt and yn equal to axn are linear system. They are both additive and homogeneous. They are both additive and not non-homogeneous. They are both additive and homogeneous. If you say axt plus b is not a linear system because it is neither additive nor homogeneous. Now you have to understand that for a linear system, the relation between the input and output should be a straight line. Not only that it should be a straight line, it should pass through the origin. Okay, so axt is yt equal to axt is a linear system. Yt equal to axt plus b is not a linear system. So not only that the input output relation should be a straight line, but that it should pass through the origin. So that is the meaning of a linear system. The same system can be, one system can be linear for one set of input and outputs and non-linear for another set of input and output. It is quite possible. Say for example, if you look at a resistor, if you look at the current as the input and voltage as the output, then the voltage output to current input relation is a linear one. It's a linear system. But if you look at, if you consider the heat output as a output and the input as a input current, then output heat produced, suppose you are using it as an electric iron, the output is I square R. So it is a non-linear relation. So when you consider heat as the output, it's a non-linear system. The same resistor is a non-linear system. So only if you are sure about the inputs and outputs, you can talk about the linearity of the system. So a linear system is both additive and homogeneous. Now what is the time invariance of a system? Now let us think about time invariant CT systems first. If the response to the input to the CT system is xt, if the response to the input CT system xt is yt, that is, I have a continuous time system to which I give an input xt, the response is yt. Now, if I delay this input by say tau units, and if the response is just y delayed by tau units, that is, the response to the delayed input xt minus tau is, if it is yt minus tau, then the system is time invariant. That is, I give some input to a system, I get some output. I give the same input after some time. If I get the same output after the same amount of time, then the system is said to be time invariant. Okay, so the time does not affect that system. So let us look at a simple system yt equal to cos xt. The response to delayed input, say x t minus 2, I mark it as a y dash t, that is equal to cosine of x t minus 2. And the delayed output yt minus 2 is cos xt minus 2. I put t equal to t minus 2 in this equation. So it is cos xt minus 2. This is the same as y dash t. So the response to the delayed input is the delayed response. The response to the delayed input is the same as a delayed response. So the system is time invariant. Now let us look at the system yt equal to axt plus b. This is a nonlinear system. Let us see whether it is a time invariant system. I apply a delayed input xt minus 2. The response will be y dash t will be axt minus 2 plus b. So the delayed output is y t minus 2. That is, I put t equal to t minus 2 in this equation. So it becomes axt minus 2 plus b. So the two are the same. Y dash t is the same as yt minus 2. The system is time invariant. Now let us consider this system yt equal to txt, where there is a multiplication by time. By looking at that, we know that it should be a time invariant system because there is a direct multiplication by t, but let us try that. The response to the delayed input xt minus 2 will be y dash t, that will be t times x t minus 2 plus b. Okay, and the delayed output yt minus 2 will be t minus 2 x t minus 2 plus b. X t minus 2, there is no b here, I am sorry, this is a mistake. Let us continue with this. Now the system is yt equal to txt. The response to delayed input is t times xt minus 2, and the delayed output will be yt minus 2, that is t minus 2 xt minus 2. So y dash t is not the same as yt minus 2. The system is time variant. Again, direct multiplication by t indicates that it's a time variant system. Now let us look at this system yt equal to x minus t, that is, it is flipping in time, it is folding in time. The response to delayed input xt minus 2 will be y dash t will be x of minus t minus 2, because it is flipping the time axis. So here xt in xt minus 2, this t axis is made negative, x minus t minus 2, and the delayed output will be, I put t equal to t minus 2 in this equation. So in this equation yt equal to x minus t, yt minus 2 will be x of minus t plus 2. The two are not equal. Y dash t is not the same as yt minus 2. So y dash t is not the same as yt minus 2. The system is time variant. Now let us think about discrete systems, time invariant discrete systems. About time invariant discrete systems, if you see, if the response to the if the response to the say input xn is yn, say I have a discrete system to which I give a input xn, the response is yn, and the response to the delayed input xn minus m, that is delayed by m units, if it is yn minus m, then the discrete system is time invariant. That is, I give some input xn to a system, then I get some response, then I give the same input after some delay, some time difference. So then if I get the same response after the same amount of delay, then the system is a time invariant system. So consider the system yn equal to cos xn. The response to the delayed input xn minus m will be y dash n, that will be cosine of xn minus m. Okay, the delayed output will be in this y n is replaced by n minus m, so I say put yn minus m, that is cos of xn minus m. The two are equal. Y dash n is the delayed response, so the system is time invariant. Now consider the system yn equal to axn plus b, that's a nonlinear system. Response to delayed input will be xn minus m will be y dash n, that will be axn minus m plus b. Now if I delay this output yn by m unit, that will be, I replace n by n minus m in this equation. So yn minus m will be axn minus m plus b. So since y dash n is yn minus m, the system is time invariant. Now let us look at the third system, that is yn equal to nx, and this is just like yt equal to txt. By multiplication by n, we know that it's a time, it should be a time variant system. So yn equal to nx, and the response to delayed input xn minus m will be y dash n, that will be n times xn minus m. And if I delay this output, I replace n by n minus m. So yn minus m will be n minus m xn minus m. So this is not the same as y dash n. So the system is a time variant. Now I have a system yn equal to x minus n. This is not x minus t, it is x minus n. Now consider the system yn equal to x minus n. This is equivalent to the discrete continuous time system yt equal to x minus t. So the response to delayed input will be xn minus m will be y dash n will be x minus n minus m. That is, I fold the time axis. Then the delayed output will be yn minus m will be x of I replace n by n minus m. So it will be x minus n plus m. This y dash n and yn minus m are not equal. So the system is time variant. Now what is a linear time invariant system? That is, systems that are both linear and time invariant are LTI systems. Both linear and time invariant. So LTI systems have great impact in system theory, signal processing, communication systems and control systems. So much of the theory we are going to learn will be around linear time invariant systems. Now the summary of understanding. Now in this video you understood what a system is, what the states are. Okay. Then you learned the additivity and homogeneity of continuous time systems with example. Then you learned the additive and homogeneous discrete time systems with examples. Then you understood the continuous time and discrete linear systems with example, that is, systems that are both additive and homogeneous. Then you understood the time invariance in discrete and continuous time systems. Then you understood the linear time invariant discrete and continuous time systems. And that is the end of this video. I thank you all.